My name is Howard Hinnant. I work for Ripple Labs, senior software engineer for Ripple Labs. And basically what I have for you today is a full day course scrunched down to 1 hour. And really, if you take questions during that hour, this is a 2-hour talk and we're gonna fit it into an hour. So I'm gonna ask you to just hold your questions to the end of the talk. And if you follow that to its logical conclusions, there really won't be time for questions after the talk either. So my apologies. I will be around all day. I love to talk about this stuff. So find me after the talk. I'm happy to answer questions. If you can't find me after the talk, search the net for my name, Howard Hinnant. My email is easy to find. I'm happy to answer questions on email. This is also talking about a GitHub project. There's an issues list on the GitHub project. Feel free to take advantage of that, or even ask questions on Stack Overflow. If you tag your question with chrono, I will see it, guaranteed. So moving on. I'm going to be discussing a DateTime library that I've been working on for about the past 6 months. This library is a seamless extension of the existing chrono library. So if you know chrono, you already know a surprising amount about this date library. And if you don't, well, learn chrono. Chrono itself, it comes with your C++ compiler. It's a great library. This library, it's minimalistic, it's very small, single header, no source, so it's very easy to install. Just include the header and off you go. I'll get the bad news out of the way up front. It won't do everything you want. However, it provides efficient building blocks so you can easily do everything for yourself that you might want to do. So in the big picture, this library sits right on top of your chrono header. It's called date.h. Oh, sorry about that. I am moving ahead. Let me back up a little bit here. Too many builds. Never put so many builds in your slides. Okay. Yeah. I probably shouldn't use this header, this pointer. Here we go. Okay. So we're going to be talking about date.h. It sits directly on top of your chrono header. Date.h does not do time zones. The reason it doesn't do time zones is because one of the big features of date.h is it is a very small library. It's a tiny library. That means it's a very fast library. And that's part of the reason that this library won't do everything you want. However, if you do want to do time zones, there's an additional library that's layered on top of this one called tz.h. I've got just a couple of slides that I might have time to talk about on that, but I'll be concentrating on date.h. So date.h is composed of basically 3 layers. At the bottom layer, there's date algorithms. On top of that, and completely encapsulated by that, are what I call type-safe objects. And then on top of that is what I'm calling the Qt API, and I'll explain all these terms. The important thing to remember is that the date algorithms, although they're in the library, they're not directly accessible. You access everything either through the type-safe objects or through the Qt API. So just as an example, here's what the date algorithms look like. This is an algorithm that converts a year, month, day triple into a serial count of days, and it's not important that you understand everything that's going on up here. There's 3 things that I want you to see. 1, it's constexpr, at least in C++ 14. 2, there's no loops in here. And 3, you never have to deal with this type unsafe API where you're only dealing with integrals. Integers don't really represent dates, they represent anything you decide they represent. And so this library hides that type unsafe API from you. Here's another example. This takes a serial count of days and goes the other way and gives you a year, month, day. It's a big mess, but it doesn't contain any loops, and it also doesn't contain any modulo operators either. During performance testing, as Chandler, if you saw Chandler's talk yesterday, modulo is pretty slow. And there's actually a couple of places in here where I had modulo and performance tested it. And sure enough, little branches are faster than modulo, at least on the architecture that I was testing on, which is x86. So every one of these data algorithms, there's about a dozen of them or so. They've been tested over a ridiculously large range, way more than it needs to be. And if you're only interested in the algorithms, that's a whole nother talk. It's got a paper devoted to it. You can go to this URL. You can read how the algorithms were derived, how they're tested, et cetera, et cetera. No detail left unturned there. So the type-safe objects. There's an object called Daypoint that is the central hub of this entire library. And then around Daypoint are all these other types that convert to or from it. Some of these types are what I call field types. That is, with a type called year, month, day, for example, this is literally holding just 3 integers. One for the year, one for the month, one for the day. Year, month, weekday holds a year, a month, a day of the week, and an integer that means this is the 2nd or the 4th Tuesday of the month or what have you. Year, month, day, and Daypoint are probably the 2 most important types in this library. As I said before, year, month, day is just a simple thing that holds 3 integers. That's what it's good at. It's all it does. And Daypoint is our serial-based time point. All it does is hold a simple count of days since the epoch. The epoch in this case is the same epoch as your chrono system clock, which is unspecified, but the de facto standard on that is everybody's counting non-leap seconds since January 1st, 1970. So the way you access the data algorithms that I told you about is you convert one type to another. When you convert year, month, day to Daypoint, you execute one of those nasty data algorithms under the hood. And when you do the opposite conversion, you execute another data algorithm. And that's the way this entire library works. You just convert one type to another to do your calendrical calculations. Finally, the Qt API is simply a set of overloaded division operators that allow you to compose field specifiers into the field-based types. For example, if I have a year, a month, and a day, I just use the slash operator, year slash month slash day, and you can think of this as a factory function to generate a year, month, day. Or conversely, if you know some of these things at compile time, there's all kinds of compile time constants in this library, and you can compose something such as this to mean the last Sunday in March for 2015, and that gives you a type that's a factory function for a type year, month, weekday, last. Now, surprisingly, some people really don't like the Qt syntax, and if you're one of those, don't worry. The Qt syntax is this optional layer on top of the type-safe objects. Everything that this does can be done with traditional constructor syntax. Here's what it looks like. If you like that API better, knock yourself out. It's all there. So next I'm going to dive a little bit deeper into the year, month, day field type. Here's how you would construct one with the Qt syntax. There's a underscore y literal to change an integer type into a year type. There's constants for each of the 12 months. This one's September, obviously. And then 25, which means today. This is September 25th, 2015. All this does is store 3 integers in this very simple struct. So there's no date computation going on when you construct a year, month, day. It's got observable fields, so what you put out in, you can easily get out. So it's very simple, very predictable, and very efficient. It's actually doing nothing, but that's useful. And of course, all of this is observable at compile time. If you want to make a constexpr year, month, day, and static assert what your fields are, that's all very doable. Everything is available at compile time. Year, month, day is the best data structure for year and month arithmetic. So if you want to add months or subtract years, that's all very doable and in all type-safe syntax. You never can add an integer to a year, month, day or subtract an integer from a year, month, day because that would be ambiguous what it means. Everything is very type-safe, and the advantage of type safety is that you catch your errors at compile time. If you want to do day-oriented arithmetic, you need to convert to Daypoint for that. And the reason for that is efficiency. If you try to do if I allowed Daypoint arithmetic on a year, month, day type, it would have to convert to the serial type, do the arithmetic, and then convert back. And instead of hiding that expense, I'm making it very explicit that you have to convert to the serial type to do that type of computation. This is kind of like the difference between vector and dec, or vector and list. You choose which data structure is appropriate for the computations you want to do. If you need to do a lot of push fronts, vector is probably not the data structure you want to use. You would use dec or list or what have you. So the same sort of thing is going on here. If you need to output these things, you get simple readable streaming. All it does is output the year, month, and day so you can see what you've got. This is mainly useful for debugging purposes. There's very little formatting or parsing available in this library. That will be a library layered on top of this. So if you don't need fancy formatting and parsing, you don't pay for it. Here's an example of doing that. Each integral type is explicitly, not implicitly, explicitly convertible to the year, month, and days and back so that you can develop whatever formatting or parsing you need to. Here, if I can read in 3 ints with no formatting at all and easily form a year, month, day object. And if, just as a little helpful syntax sugar, only the first field needs to be explicit if you want to get lazy. That's optional. If you specify the first field as a year, then it becomes unambiguous that the next field has to be a month and an integer is acceptable there. And the next field has to be a day. If for some reason you're allergic to the year, month, day ordering, day, month, year is also okay as long as you specify the first object as the day. And month, day, year ordering is also okay. It's commonly used in the US. Now, only those 3 orders are okay. And why did I pick only those 3 orders? It's because those are the only 3 orders that people actually use on this planet. Tough choice.
So you're cutting out all the alien users.
Exactly.
Oh, man. What do you hate aliens?
Now, if you accidentally type one of the alien orders, or if you accidentally do something that would be ambiguous, this is an error that's caught at compile time. And I've got complete unit tests to make sure that I'm catching every single combination at compile time, and only the good ones are coming through. So if you write something and it compiles, it will both be correct and readable. So one of the first things that everybody asks when they see a new date library is, how do you handle invalid dates? Specifically, I've got the last day in January, I'm going to add a month to it. What do you do? And every library has their own different thing that they like to do about this. And they're all reasonable answers. Some libraries will assert you can't do this, or throw an exception. Or some libraries, like the Boost library, will snap to the end of the month, and that's fine. And still other libraries will overflow into the next month. There's all kinds of ways of handling invalid dates. And these are all great choices, and I've chose none of them. What I'm going to do is push this decision onto you. This library is a fundamental building block that's very efficient on the bottom, allowing you to do whatever you need to do. You can choose any of these. And I'll show you exactly how you can choose them. What this library actually does do is allow you to construct invalid dates. Now, I'm going to show you later that this is actually a very powerful feature. It can actually make the code more readable and add more performance. And I know that may be hard to swallow now, but just hang with me. By the end of the talk, I hope to convince you of that. So let's say that you just wanted to add a month and make sure it's a valid month. Every field type comes with a member function called OK, and all it does is say, am I a valid date or not? So if you've got January 31st and you add a month to it, the year, month arithmetic only manipulates the month and the year fields of the year, month, day. And later you can go back and say, is that a valid date? Is it okay? And that will either return true or false. And you can assert on that. It's as easy as this if you want to assert. So naturally, if you want to throw an exception, it's practically the same thing. You check OK. If it's not OK, you can take your time, format up a really nice error message and stuff that into an exception and throw it, and off you go. But how do you talk this library into snapping to the end of the month? Well, that turns out to be incredibly easy too. If you add the month, turns out not to be okay. You can construct a new year, month, day by taking the current year, the current month, and appending it with this keyword, well, this operator called last. And that literally means whatever the year and the month is, I want the last day of that year, month, day, assign it back into YMD, and voila, you're at February 28th. Or if it's a leap year, the 29th, sure. So, what if you want to overflow? It's a little bit trickier, it's not as obvious, but it's just as easy once you learn the trick. You take your year, month, day, if it's not valid, you serialize it into this serial count of days called Daypoint. Now, every Daypoint is valid. It's just a count of days. It's just an integer under the hood. And when you deserialize that back into a year, month, day, you'll get a valid year, month, day. And in this case, if you jump from February 31st, 2015, that will convert into March 3rd. So you've got all your options available to you. And errors are either caught at compile time, for example, if you've got an invalid ordering or an ambiguous ordering with the YMD construction, or they're caught at runtime with OK. The library itself does not check OK at all, not even once. It's up to you to decide how often and where you want to check OK. That means you may sometimes have logic where you're always adding a month, and you know that the day can't possibly be above 28. And so you might not want to check OK. So you can save cycles. Everything here is about safety, performance, and ease of use. Sorry, I just said that. So this library also does not throw exceptions, with the possible exception of when you insert into a stream, the stream may throw. But besides that, this library doesn't throw any exceptions at all. But it's completely exception safe, of course. So you can throw exceptions whenever and however you want to. It leaves the decision of how to handle errors completely up to you. It's error neutral, so to speak. So I'll briefly mention this last thing. And it turns out that wherever and whenever it is legal to specify a day, it's also legal to specify last. And you can do it in any of the three orderings, year, month, day, month, year, month, day, year. It doesn't make any difference. These are all expressions that create a type year, month, day, last. And the API of year, month, day, last is virtually identical to that of year, month, day. It's got a year observer, a month observer, a day observer. It is even implicitly convertible to year, month, day. So we saw this code earlier where I jumped to the last day of the month. We're actually forming a different type here with the year, month, day, last, but we can assign that back into our variable of type YMD, which had type year, month, day. And you don't even realize you're changing types. It's an implicit conversion. It's also a very efficient conversion, and it does exactly what it looks like it's doing. So very easy to use and very efficient. It turns out that wherever you can specify a day in the year, month, day ordering, you can also specify an indexed weekday. So here, these are three ways of saying I want the fourth Friday in September of the year 2015, which happens to be today. The type of each one of these expressions is year, month, weekday. And year, month, weekday is a very simple field type that simply stores a year, a month, a weekday, and an index, 1 through 5. It's as simple as that. When you construct one, absolutely nothing happens, but those four fields are stored. So as you might imagine, again, it's very efficient. You can print it out and you can get these four fields, or you can convert it to a year, month, day object. And now you're executing one of those date algorithms, low level under the hood that I was telling you about. And now you can get year, month, and day of the month. It's as simple as that. So you've got very high level access to these very low level complicated algorithms in a very type-safe manner. It turns out that you can also index weekday with last. So here are three ways of specifying the last Friday of September of the year 2015, which, surprise, is today. This is another field type. It's called year, month, weekday, last, and all it does is store a year, a month, and a day of the week. So when you construct one of these things, absolutely nothing happens except storing three integers. You can print it out and find out what three integers are in that field. You can explicitly convert it to year, month, day. Are you guys beginning to catch on a little theme here? This library is very self-consistent, making its API conceptually very, very small. So you convert it, that'll execute one of these date algorithms under the hood. You can print that out, get your 3 fields, and you're good to go. So that's a rough view, quick tour of the field types. Daypoint is what we call the serial-based type, and it's serial-based because under the hood, it's nothing but a count of an integer. And just like it's important for you to understand what's under the hood of a vector or under the hood of a list, I think it's important for you to understand what's under the hood of each of these data structures. And Daypoint just holds an int. It's a count of days since New Year's 1970. Daypoint is actually a standard chrono time point. As I said, it's a simple count of days. And in the library, this is exactly how it's specified. So Daypoint, I've told you, is the central theme of this library. And it turns out that the central theme of this library is nothing more than a type def for a type that's already in your standard library, in the chrono header. So that's a little bit remarkable. How do we create a Daypoint? It's very easy. You create a year, month, day, and that is implicitly convertible to a Daypoint. So here we've created a count of days since September 25th, 2015, today. Since it's a chrono time point, it has this member function called time since epoch. That's going to return the duration type within the Daypoint, which naturally is days. Days is just a type def for another type of duration in your chrono library. Happens to be defined to 24 hours, surprise. And you'll get, wow, it's been 16,703 days since the epoch. How exciting. As you might imagine, since all this thing does is hold an integer inside, day-oriented arithmetic is incredibly efficient on this type. If I add 2 days to it, all it does is bump up that internal count by 2 days, and it's as simple as that. So we're talking very high performance here for day-oriented arithmetic. Other date libraries like Boost Date Time or like the Bloomberg Date Library, all they have is Daypoint, but they'll call it something like date. But internally, all they're doing is exactly this. And so day-oriented arithmetic is fast on their libraries too. But year, month, day arithmetic is slower because they're converting back to the YMD format to do the year and month arithmetic. So Daypoint is a time point just with a course duration. It is a system clock time point. Now, system clock time point is actually going to be something with a duration of microseconds or nanoseconds. It depends on what platform you're running on. And Daypoint is very closely related to that. It's the same thing, just translated to have a coarser duration, that of days. The chrono library has something called time point cast that allows you to convert a fine resolution day point to a fine resolution time point to a coarse resolution time point. And that's all this is doing. You can use the existing time point cast conversion function that comes with your chrono library to convert the output of system clock now to a day point. So if you want to find out what day it is, call system clock now. If you run that right now, it'll give you the current time. Now there's one disadvantage of time point cast, and that is that it truncates towards 0 always. Now that's exactly what you want when you have a positive time point. But for negative time points, it truncates upwards towards 0. And you get negative time points when you deal with days before the epoch, that is before 1970. So I'm creating a new rounding mechanism that's called floor, which rounds towards negative infinity so that it actually gives you the expected results for all time points, not just those after the epoch. It's just as efficient as time point cast. In fact, it actually calls time point cast and then does the rounding for you. And so I favor using that. If you don't like floor for some reason, you can always use time point cast and it'll work exactly as you want as long as you stay after the epoch. But I like floor because it's easier to type, it's easier to read, and it always gives the right result. So what does this look like? We call now. We look inside with the time since epoch method, and we run this today, and we'll get 16,703 days again. It's as simple as that. So how do we deal with dates and times? Well, it turns out that you've already got in your standard library a wonderful DateTime type, and it's called system clock time point. And Daypoint is just another version of system clock time point. So I'm going to leverage all of this out of the chrono library to just glue all this calendrical stuff and date time stuff together. So in this example, I've got a time that is just 2 days after the epoch, and that's just to make the arithmetic very easy. As you saw before, I can create one of these things, print out the time since epoch, inspect it, see that there's 2 days in there. If I want to, I can simply add hours to it as easily as this. In C++14, there's user-defined literals for all the durations, hours, minutes, seconds, nanoseconds, etc. So I can take this day point and add hours to it, and all of a sudden, I've got a time point that has the duration of hours instead of days. I can look inside of it, and I've got 48 hours for the 2 days, plus another 7 is 55 hours. It's as simple as that. I can add minutes to it. I can add seconds. I can add nanoseconds. You can add any duration you want to it. There's no limit. For this slide, I've stopped at seconds just to make it not too crazy, and so everything would fit on one slide. You can look inside this thing and find you have 200,000 seconds, which coincidentally is 2 days plus 7 hours plus 33 minutes plus 20 seconds. So in one line here, I've gone from 6 field types down to a serial count of seconds since the epoch, all in one line, and all very easy to read. Very nice calendrical computations going on under the hood here. Okay, now that I've got this count of seconds since the epoch, how do I go the other way? How do I recover these 6 fields from this 200,000 seconds? So you first can recover the day point with the same way that I've been showing you before. This is nothing but another time point with a duration of seconds this time. Take the floor of it, I'll get a day point, I'll look inside under the hood, there's 2 days in there. So that's not quite what we were looking for. However, day point can be thought of as a time point to the very first minute of a day. So if we take this fine precision time point, TP, and subtract from that the coarse precision day point, time point, DP, you get the time since midnight. Now you get it in seconds, but we'll deal with that. But it's very intuitive once you know the tricks. You want the time of day, you subtract the current time minus the time that corresponds to midnight. Simple as that. There's a factory function called makeTime. It'll take any duration you have, whether it's nanoseconds, seconds, hours, what have you, and it'll break it down into a field type, in this case, hours, minutes, seconds. So I take my difference, send it through makeTime, I get the structure out. Now I've got field observers for my hours, minutes, seconds. Lo and behold, I've got 7 hours, 33 minutes, 20 seconds, just like I had up at the start. We still haven't recovered our year, month, day, but you already know how to do that. You take the day point, you convert it to a year, month, day object, and now I've recovered my 3 fields for the day. So I've gone full circle, almost all on one slide. I had to scoot things around a little bit. If my slide was a little taller or made the font a little smaller, I could fit it all onto one side, but I wanted to make sure you could read it. So I preferred the sliding solution. Much of what I've just shown you already comes from the chrono header, even both the interface and the implementation. If you happen to be somebody that already knows chrono, you'd be saying, you're not really presenting anything new, that's all chrono library, and you would be exactly right. So if you want to learn this library, learn chrono first. And then when you come to this library, you'll just say, well, yeah, this is barely even a library, and it really is. This is what makes it small. This is just a very small extension on top of chrono into the realm of calendars, mainly the year, month, day type, and these type defs for day point and days is really all this is. So how expensive is all this? Good question. Glad you asked. So instead of running timing tests, what I'm going to do is show you a couple of examples that are very small functions, and I'm going to code them 2 ways. I'm going to code them one in a very low-level C-like way, and then I'm going to code them again using this library. I'm going to compile the code with optimizations turned on and show you the assembly. And don't worry, I know everybody doesn't know how to read assembly. I'm not that great at reading assembly myself, but the examples are going to be short, and I hope to be able to show you what you need to know without needing to be an expert in assembly language programming. So I'm going to start with a very simple YMD struct. Here it is. It's got a 16-bit year in it, 8-bit month, 8-bit day, very simple thing, and I'm going to make a factory function for it. And all it does is takes 3 ints, stuffs it into this thing, and returns it. Now, how do we do this same functionality in the date library? Well, as I showed earlier, I prefer the Qt syntax. You could use the traditional constructor syntax if you prefer, but you take 3 ints, you explicitly cast at least the first one to a year, month, or day, and then you add the others, and you can return that, and that'll be a year, month, day object. So compile both sides of this down to assembly, optimized assembly. Let's see what we get. Here we are. We get virtually identical assembly generation. Up at the top, you can see that I've got different mangled names. So what? And if I gave you enough time to stare at this, you would see that the ORLs, the ORLongs at the bottom, they're switched in order. And that's it. This is virtually the same assembly. There is absolutely no space overhead and no time overhead for this Qt syntax or for this library, at least for constructing year, month, day. One more example here. This one's a little bit more involved. I've got a situation where I'm measuring seconds since a different epoch. I want to measure seconds since the year 2000 instead of since 1970. Why? Well, that's just what I want to do. It's my employer made me. Here's how you might do it in C or low level. You'd store your time point in a long, and then you'd go off to the side and you'd say, okay, how many seconds are there between New Year's 2000 and New Year's 1970? You'd go off and you'd compute all that, and you might even get the right answer, and then you'd add it to your time point to shift from the year 2000 back to the year 1970. How do you do it in this library? It's a little bit more verbose, but it's a lot more type safe. I'm not going to store my time point in a long. I'm not a Neanderthal. I'm going to store it in a chrono time point. I'm going to use system clock as the clock and say, specifically specify that I'm using duration seconds. So now I've just got a count of seconds. And I'm going to add to my count of seconds the difference in time between January 1st, 2000 and January 1st, 1970. So yes, it's a lot more verbose, but I've taken one magic number and turned it into 4 magic numbers, and then all of a sudden it's a lot more readable. The 4 magic numbers over here, you know what they are. They're the day and the year. It's very obvious. Yeah, well, I hope it's obvious. Right. So how much does this cost us? Let's compile both sides. Optimization's on. Take a look. It's identical. It's absolutely identical. You can even see the magic number on both sides, the 946 million seconds or whatever. It's on both sides. So let's take another look at that. How did that actually work? Over here, we've got to serialize both of these days, convert them to days and subtract them to get 10,000 some odd days. Convert that to seconds because the compiler knows I'm adding days to a time point based on seconds, so it just does that automatically. And it's doing it all at compile time. This is amazing. This is where constexpr really comes in. Even though there's no constexpr anywhere visible in this user level code, constexpr is helping the compiler do all of these computations at compile time, creating efficiency equivalent to a silly, well, maybe not silly, but obviously efficient C implementation of this function. So let's do a little bit of runtime experiment. To do runtime experiments, I've chosen 2 other victims, the Bloomberg library and the Boost DateTime library. And I'm terrible at names. I don't know what we're calling this, date.h or whatever. And just as an example for demonstrating the runtime performance of this library, I developed a problem. I want to throw a party on the 5th Friday of every month that has one. So I'm going to write a function that takes a year as input, and I'm going to go through all 12 months of the year, and if the month has 5 Fridays, I want to print out that date and send out invitations. And I'm going to do it for each of these 3 libraries, and my questions are, how easy is this to code? And how expensive is it at runtime and also in code size? For those watching this talk on video afterwards, I'm putting all the details of exactly how I'm doing this test so that you can go home and reproduce this on your own computer, just to make sure that I'm not making things up on the sly. So I'm inputting a year to this function right here as just an int. And then for output, I've just made a homemade struct. Now, if this were production code, I would obviously output this in whatever native format that the DateTime library happened to have. But so that all 3 of these libraries are having to do the exact same thing, I'm standardizing my output and input like this. And since there's going to be, I'm going to put all the dates in a standard array of length 5, and then I'm also going to pass back the logical length of this array, which is always going to be either 4 or 5, because it turns out that there's always either 4 or 5 Fifth Fridays in a year. I'm doing everything at -03. Here is the driver I'm using, and Fifth Friday up here is the function that I'm actually timing. I'm wrapping that with steady clock now. I'm going to read my year in from the terminal, and the reason I'm doing that is because I know my library is very aggressive at computing everything at compile time. If I told it to, it would compute this whole thing at compile time without me even blinking, and then we wouldn't have anything to measure. So I'm reading in the year to make sure that that doesn't happen, and then I'm printing out the results just to make sure that the optimizer doesn't optimize everything away that I'm trying to compute. And then finally, I'm printing out my count. And for my platform, steady clock now traffic's in seconds. I think that's true for every platform. I'm not positive, but at any rate, so we'll get output that looks like this. It'll print out the days and then the time and the nanoseconds. And I also discovered that if I read my year in from a file, that I got much more consistent results than if the program was waiting for me to type everything on the keyboard. So I put the year 2015 into a file, and I'm executing it like this. Oh, and one thing I forgot to mention on the previous slide. I'm actually going to run this 2 ways. This is exactly how I'm running it for the first way, and this is called the cold cache run. I'm only going to execute it once, and I'm going to run this 10 times manually and give you the average of those 10 times. But then I'm also going to do a hot cache run where I'm going to put 1,000 calls to Fifth Friday in between the 2 statements from now, time that whole 1,000 calls, and report back 1,000th of that call, so you can see what the hot cache results look like. Because it makes quite a bit of difference whether we've got everything in memory, in the memory cache, or whether it's got to go all the way back out to RAM, which is very slow, as some people may have told you in talks earlier this week. So moving on, what does this look like? Oh, and disclaimer, this is not a complete comprehensive test. This is just one little small test just for this talk, so take it for what it's worth. I sent this problem off to John Lakos at Bloomberg, and I gave him code how I thought it should be coded, and I said, look, John, I really don't want to present your library in a bad light. Am I doing anything stupid here? How would you code this problem up with your library? And it really got out of hand. He gave it to his engineers, and they worked on it for like 2 days. And they sent me back this. What they did is they realized that there's only 14 answers to this problem. There's only 14 calendars. January 1st can start on one of 7 days, and you can have either a leap year or a non-leap year. And once you know all those things, you know the answers, and these are the answers. So I really didn't intend for them to do it this way. I was actually trying to measure something that was something people might actually code up as opposed to this. But it was interesting nevertheless, so I wanted to present it. And so it's not important to understand all the details, but basically they're seeing what day of the week January 1st is on and whether it's a leap year or not, and then they just look up the answer in the table of 14 and spit that out. So you might imagine that this is very fast. You really can't get any faster than this, so it gives us a lower level to aim for. So code size, it's about 132K. That's measuring the entire application, not just Fifth Friday, and the reason I measured the entire application is because some of these libraries are header only, some aren't, and I needed to do something that was the same for everybody and be fair. So I chose the entire application. And this clocks in at just under 3 microseconds for the cold cache run, and for the hot cache run at an amazing 189 nanoseconds to calculate the 5 Fridays in the year 2015. So very impressive. Congratulations, Bloomberg. And I'll just admit right up front, on the hot cache run, nothing gets faster than that. You just can't get faster than pre-computing all your answers and looking it up in a table with a hot cache. So they win. I admit defeat. Next, I sent this off to Jeff Garland, who wrote Boost, and he sent me back a couple of suggestions to do it a little better, and I've incorporated those here. And I'm doing more what you would expect here. I'm simply, you get the year from the input, you loop over the 12 months. Boost has this nth day of the week in month where I can ask for the 5th Friday of the month, get the day out of that. Now, Boost does an interesting thing here. What if the month doesn't have 5 Fridays? What they do is they say, oh, you must have meant the 4th Friday. Okay, I can deal with that. So when I get my answer back, all I've got to do is figure out whether it sent me the 4th Friday or the 5th Friday. And if you sit down with a pencil paper and a calendar, you can figure out, well, if it's the 4th Friday, the day of the month is always going to be less than 20, it's going to be 28 or less. And if it's a 5th Friday, the day is always going to be 29 or greater. So I'm using that to figure out if I've got a 5th Friday or not. And if I do, I push it onto my stack of results and I move on to the next month. Boost is header only, so the code size comes in impressively lower. The cold cache time is about twice as much. That's really not that bad. It's actually computing things at runtime instead of looking things up in a table. So when you think about it, that's really a fairly impressive result for Boost. And if you warm the cache up, you get down to under 2 microseconds, so we're doing good there. Now, after I sent this to Jeff, he said, hey, I'm working on this Boost DateTime version 2. And I said, really? Is it close enough to test? And he said, well, it's still under construction, but yeah, you can test it. I don't mind if you present it, so let's take a look at that. The syntax is a lot nicer, and actually, it's quite similar to what I'm doing, except with some renaming, but he's got a year, month, day object there too, just like I do. The accessor for day is a little bit different, but we're just talking syntax here. It still has the same semantics. If you ask for the 5th Friday and it doesn't have one, you get the 4th. So same logic going on here. And let's see how it did. Understand that this is still under construction. In fact, to run this, I had to include both the V1 libraries and the V2 libraries. Give Jeff a break. He's working on it. So the code size is a little bit bigger because I'm actually using both Boost V1 and V2. And correspondingly, the cold cache run is a little bit slower. It's caching in more code as well as more data because it's using 2 libraries. And so the cold cache runs really aren't that surprising. The hot cache runs come right down to where you expect, even a little bit faster than Boost V1. So that looks very good. So, okay, let's get on with it. How do you do it with this library? First, I find the last Friday of the month. Just like this, using the cute syntax that I prefer. And then if you recall, I've got this thing called year, month, weekday, which stores an index as one of its fields. So I take my year, month, weekday last, and I don't have to spell that ugly type anywhere, convert it to a year, month, weekday, ask it for its index. It's going to come back as either 4 or 5. If it's 5, I've found a 5th Friday, and I'll push it onto the stack. To do so, I need to convert it to a year, month, day object so I can get a day of the month out of it. But beyond that, we're good to go. So I actually find this more readable than the Bloomberg library, believe it or not. I also find it more readable than the Boost library because I don't have to know what the policy is here on what happens if the month doesn't have 5th Fridays. The Bloomberg library, actually, if you ask it for the 5th Friday and the month doesn't have one, it overflows into the next month. It gives you the 1st Friday of the next month. So there's all kinds of policies that you need to be aware of depending on the library that you're using. Here is code that's policy neutral. You don't have to know. Give me the last Friday, tell me whether it's the 4th or 5th. It's as simple as that. So what do I pay for that convenience? Code size, tiny, 15K. Runtime size, cold cache, fastest yet. Wow, think about this. Cold cache, it is faster than pre-computing the answer into a table and looking up the answer in that table of 14 things. How can that be? The reason for that is code size. I told you at the beginning of this talk that this library won't do everything you want. That's not a bug, that's a feature. That's how you keep it small. That's how you keep it fast. Very small code size. You warm up the cache and you don't get a huge boost because there's not much to cache in. There's not much difference between the cold cache and the hot cache performance. But it's very respectable. In a real application, you might not have a hot cache. Real applications don't spend their time finding the 5th Friday of the month all the time. You've got other things to do. And in a real application, your date computations are just a tiny part of your real application. So I think that your cold cache measurements here are actually very important. So this date library could conceivably be faster than the pre-computed Bloomberg solution that Bloomberg gave me. But I'm not quite finished. There's one other way that I want to show you. Since it's my library, I get to show you 2 ways for my library. Let's just go ahead and ask for the 5th Friday. I don't know whether the month has the 5th Friday or not. We'll just ask for it. What does this library do? It's very self-consistent. It just stores the numbers in a field. Then I can say, by the way, did I create an OK date? Is this valid? If so, convert it to year, month, day, store it. If not, loop on around to the next month. For readability purposes, this one's my favorite. Opinions may vary. If you like the previous one better, go with that. You're not going to do very bad. Okay, but let's say that we like this one. How much is it going to cost us? Code size, it's not going to cost us anything. Runtime size. Our cold cache run is now as fast as our previous hot cache run was, and our hot cache run is getting competitive with the Bloomberg solution. I think we're so about 220 nanoseconds or something like that compared to 189. It's in the ballpark. I find that impressive. I was pleased with this result. Even though they beat me, I was pleased with this result, knowing the way that they computed their runs. So there's 3 things I want you to get out of that performance test. Date.h is small, it's fast, and the ability to create invalid dates without being scolded with an assert or a throw or with some approximation of, oh, you meant the 4th, or oh, you meant the 5th Friday, or whatever. The ability to create that invalid date is both a readability and a performance advantage. So if that's the only thing you remember out of this whole talk, I think that 3rd bullet right there is the most important thing to remember. Let's see. From the C standard. If you go to the C standard and read about make time and struct TM and all that, they've got in the C standard this question, what day of the week is July 4th, 2001? And just because I was in a good mood, I thought it'd be fun to compare how they present to do it in C with how you can do it in this library. So let's take a look. I'm not going to review all this code because you guys already know C, right? It's a little bit easier with this library. You use the Qt syntax, you construct a weekday, you print it out, boom, you're done. It's practically a one-liner if you don't count the using declaration and the includes. And if you want to show off, yeah, all my inputs are compile time. You can do it at compile time. At least in C++ 14. The library will auto-port to C++ 11, but that means erasing a lot of the constexpr, so you lose a lot of your compile time computing ability. I've got a little bit of time left, 10 minutes, so I want to give you just a couple of slides about the time zone library. This isn't going to be a complete thing. Basically, what I want you to get out of this is just for you to know that it exists and get some kind of feel for how it might work. It's got this function in it called locate zone, and it works with the IANA time zone database, so it uses all those names. You send it whatever time zone you want, locate it. You take your system clock and you floor it to milliseconds. I could have taken nanoseconds or hours or used any duration I wanted to there. You'll get a time point, a system clock time point, but with milliseconds duration in this example. send it to the zone's toLocal member function, and it will give you back a pair of a time point and an abbreviation for that time zone. So here I just print out both things of the pair, and I get what should be very close to now. Hey, I'm only a minute off. That's, yeah, it's not bad, hey? That's magic. So it prints out magically now and PDT for Pacific Daylight Savings Time. So if you don't want to have to always specify a time zone, you can, of course, get the current zone. On this slide, only the first line is changed from locate zone to current zone, and from there on, it works just the same. This is a parser for the entire IA time zone database history, which has time zone information dating back all the way to the 1800s. So here, just as an example, in this same time zone, the time zone we're sitting in, I look back at February 10, 1942, and print out the time for that. And if you do the arithmetic, it turns out that they went to daylight savings time in the middle of the winter for this year, and they called it wartime instead of daylight savings time. This is World War II. So, might not be practical, but for time nerds like me, I find it really interesting to be able to explore the entire history of time zones, not just for this country, but all over the world. This is a wonderful database, and so to give it what it deserves, I made a very complete parser on it. It also includes leap seconds in the database, and there's facilities for computing with leap seconds if you care to do that. I think one should resist computing with leap seconds for as long as possible, because usually when you do it, it's error prone, and you may not be getting more accuracy than you were after. So use the leap seconds with caution, but it's there if you need it in the time zone library. So in summary, I've presented a high-performance, minimal API extension made to Chrono, enabling easy and intuitive calendrical computations. It doesn't do everything everybody wants it to. This is not a kitchen sink API, but it should enable everyone to build on top of it and do whatever they need to without any performance motivation to not use it at all. It's a good base to build from. There's a complete paper on it at this URL, and this paper has links to the GitHub URL where the library is actually located. This is just the documentation. The documentation includes a bit of a tutorial and a complete reference of every single type. It's very well documented. And it also includes links both to the algorithms paper I mentioned earlier, if you want to look at how the algorithms were put together, and to the time zone library if you want to go up the stack and look at that. And finally, I'd like to acknowledge that this library was not written in a vacuum. Stefano, Alistair, and John wrote this very fine paper several years ago in 3344, which very much influenced the design of this library. This paper is essentially what convinced me that I needed to provide my clients both with the serial type and with the field types so that they can do what they need to do in the most efficient way possible. And also, Jeff Garland's boost date time has been a tremendous influence on this library. I'm very grateful. In fact, the chrono library was highly influenced. It was directly derived from boost date time. So all of this stands on the shoulders of Jeff Garland. And the constexpr work is just critical to making this thing scream fast. Even though you might not have a compile time date that you need to use, maybe you've got a few compile time pieces, like 5th Friday. Those are compile time numbers, and that contributed to the speed of this thing because it allows the compiler to propagate those constants all that much better. So kudos to Richard Smith and Gabby and Bjarne for doing all that work with constant expressions. I'm extremely grateful. So we've got just a couple of minutes left over. I'm done with my talk. I'm open for questions. Yes? Oh, no. I'll let you choose whoever's going to.
Chest. Can we have audio here? I'm not muting. You may just go ahead and speak up and then repeat the question.
Does this library contain anything for just month, day?
It has an...
Please repeat the question.
Oh, does the library have anything for just month day? It has an object called month day, yes. And it just stores a month and it stores a day, and so you can use that if you need to as a partial date. Yes.
Why is that OK function faster in the comparison? I'm curious.
To tell you the truth, I'm still studying up on that. I've looked at the assembly. It's about 500 lines of assembly, and I haven't gotten all the way through it. And so if I gave you an answer right now, I'd be purely guessing. My best guess is it's propagating the constants. And to tell whether the month is okay, it doesn't have to do quite as much computation, and it's reusing that same computation inside the if, where I convert it to year, month, day. I'm guessing. That's not a definitive answer. Won't need to access the what? Yes, you need to access the index. Yes.
Back in your slide where you showed the check on OK to detect an invalid date and then you make a correction to it, what happens if it's the middle field that's invalid? In other words, if you don't know which field is invalid, can you explain to us the process for checking that?
Sure. So the question is, what happens if it's not the index field that's invalid, but say the month or the weekday that's invalid? You can get, there's getters for every field, and then each of those individual fields has an OK member function on it. So if you were paranoid, you could go through and say, is the index OK? Is the day OK? Is the month OK? Et cetera, et cetera. But ultimately, you still have to ask if the entire collection is OK, because 5 is a valid index, although it might not be valid for the month of May 2015 or what have you.
Have you considered submitting it as a standard or to boost so they don't have to come up with V2?
Right. I am considering it. I don't think this is yet mature enough to submit to the standard. I'm waiting on you guys to tell me whether you like it or not and whether you'd like to see it in the standard. So I'm glad you asked that question, and I want you guys to answer it and get back to me.
Hi, thanks for the thing. It looks really, really cool. And did I get it correctly that you don't use anything like ICU for the time zones?
That's correct. This is going straight to the publicly available IANA time zone database, and I'm parsing that.
There's time for one more question.
I don't want to take the last question, so I'll just be fast. I saw a floor of, type, system clock, : now. I wonder if there's room for some syntactic sugar there. I mean, I guess a client could write that themselves, but, like a today or a now of this that just didn't make you write the floor. That was the one thing that looked a little off-putting, and you mentioned it yourself.
I am certainly open to discussion on all parts of this, except maybe for making it bigger. So, yeah, if we want to tweak the syntax, I'm very open to that. All right. One more question? Okay.
This should be a quickie. When you said that the times are by default by implicitly UTC, are they actually UTC or just agnostic to the actual time zone?
Technically, they're Unix time, which is a count of seconds since 1970 minus a leap second, or a count of non-leap seconds. So
Well,
almost UTC.
Thank you. It's a beautiful, elegant library.
Thank you very much.